Hello everyone, welcome to today's webinar. We have Stuart Nicol, Senior Metallurgist at Glencore Technology. Dr. Stuart Nicol is a Senior Metallurgist in Pyrometallurgy at Glencore Technology, specializing in the Isasmelt and related technologies. With over 10 years experience in pyrometallurgy, Stuart has experience in both the design and operation of metallurgical plants across multiple commodities and processes. He earned his PhD at the University of Queensland in pyrometallurgy, focusing his research on phase equilibria and reaction kinetics applicable to industrial operations. Stuart's current role includes the development and study of basic and detailed engineering projects and site construction and commissioning for the Isasmelt, Isoconvert, PBOC, and other Glencore-related technologies. Some quick housekeeping. You are muted. This is to keep things quiet for the webinar. Ignore the raise hand icon. Use the Q&A for any questions. Feel free to ask any questions along the way. Once the presentation is over, we will still be on air answering any questions you may have in the text. Over to you, Stuart.
Thanks for the introduction, Neil. As mentioned, I'm Stuart Nicol and I'll be giving the webinar today, and this particular one's on process flowsheet options using Isasmelt technology. So first up, this is a common question we get asked, and clients commonly say, hey, can you give us a flow sheet? And they say, what's your standard flow sheet? But the problem is there's no real standard flow sheet for a copper smelter. A lot of the time, most smelters, copper smelters, lead smelters, they're customized for every specific location. So it's important to take this into consideration. There's not a standard one. But in addition to this problem as well, a lot of companies will assess a flow sheet, a standard flow sheet, but they won't take into consideration all the permutations, the mixes, the matches, the things that can go on. So even though that there are Isasmelt plants out there that have got an Isasmelt furnace, each Isasmelt plant is completely different. And there's a lot of work that goes into customizing, optimizing, looking at what the parts are and what they do and don't do. So if you go to a common consulting company and you ask them to assess different flow sheets, they'll give you the standard flow sheet, but that's not necessarily the best flow sheet. Like Mr. Potato Head there, a lot of smelters you can mix and match. You can change out your equipment. You can choose different waste heat boilers. You can choose different settling furnaces, different effluent treatment plants, different dust plants, different minor element plants. There's a lot of mixing and matching you can do. And so all the time, all the plants have mixed and matched them differently, and they do this for a variety of reasons. If you just pick a standard flow sheet from another site, another location, you will have a higher Capex, a higher Opex, you'll have suboptimal chemistries, and you'll have generally lower metal recoveries than you could be, and the chemistry is not tightened and optimized for your specific location. So it's important that you do optimize and assess and refine this. So I'll sort of step through some of this process and some of the options. Specifically, I'll be talking about a primary copper smelter, but all the options and decision points you have to make for different parts of the plant apply to other commodities and flow sheets as well. So if we look at the primary copper smelting flow sheet, there are a number of steps, stages and bits of equipment to them. So while we've got the primary smelting furnace, which is the Isasmelt furnace, everything else, there's a lot of optionality. So the first stage after the primary smelting furnace is your settling furnace. People could generally choose between an RHF or an MSEF for settling the furnaces. Then you can take the slag and hand that in different ways. You can granulate, you can slow cool, you can do flotation. Then of course the primary off gas, you've got different waste heat boiler configurations. You've got conventional waste heat boilers, you've got radiation and spray convection sections, you've got radiation tubes. There's all sorts of options for your gas cooling and dedusting there. And then again you have your converting furnaces and the different options there. You've got the Pearson converters and the Isoconvert. And again on the converter, when you produce your converter slag, there's a whole host of options of different things you can do there. You can do molten slag cleaning, you can reduce the slag, you can slow cool and do flotation, you can recycle back into the primary smelting furnace, and of course the dust as well and the minor element controls. So there's a huge list of optionalities in the flow sheets, and picking out and mixing and matching the specific options you have for each location and project is very important. And what might make sense in one plant might make sense in another plant. So first up, the primary smelting furnace. So we generally recommend the Isasmelt furnace for a variety of reasons. But first up, how does the technology work? So the Isasmelt furnace is a bar smelting furnace. It has a cylindrical steel shell with a refractory brick lining and a central lance. Feed material is poured into the furnace through a feed port in the top, and that falls into the bath where it reacts. In the furnace, we inject gases down the lance. So that lance can have oxygen-enriched air, and it can operate anywhere from 21 through to 90% oxygen enrichment. You can also inject fuels in the lance as well for temperature control. Now, the feed materials react with the lance gases to generate your molten bath products as well as gases. The lance itself is immersed in the bath, and you've got the gases that travel at velocity down that steel pipe which chill it, which enable us to form a stable freeze lining on the pipe, protecting it from the aggressive conditions in the furnace. The off gas is collected from the top of the furnace and sent through your gas cooling systems, typically waste heat boilers, dedusting systems, typically ESPs for primary copper, and then gas treatment, so things like sulfuric acid plants or scrubbing systems. The molten bath, as it builds, is then periodically tapped from the furnace. So we've got tap holes in the base of the furnace where we extract the molten bath materials and we send it for downstream settling. The furnace is continuously controlled with a control room operator who continuously monitors the process and the plant. So that's just a brief introduction on how the Isasmelt furnace works. Some of the key advantages we have got for primary copper smelting is it has got approximately a 30% lower Capex. It has a 10% lower Opex for typical locations and jurisdictions. It can vary a bit there. Currently, it's the lowest emission smelting technology. Fast ramp up, long campaigns, low annualized campaign costs. It's got long lance lives, 40-day record at some sites, as well as low cost maintenance. But that's just the primary smelting furnace. If we look at most modern smelters, one of the first and most important decision points that people make has got to do with environmental permitting and emissions. So this is one of the first things that people assess. So for a certain specific location and jurisdiction, people have to meet the local emissions limits, and there are a variety of ways you can meet them. So people achieve this with tertiary, secondary, and more advanced hooding options. But if you look at the raw emissions from your smelting furnaces, different technologies have got different inherent levels of emissions. So if you look, the Isasmelt furnace currently has the lowest level of fugitive emissions in primary copper smelting, and this can be extrapolated to other commodities as well. You look at other batch converting furnaces like Smith converters, without advanced hooding, they emit a vast quantity of sulfur. Currently, if you look at base metal smelting technologies, the cleanest Isasmelt site has the lowest sulfur fugitive emissions around the world. But it is important to note that not all sites with the same technologies have the same level of emissions. And you can see that with the Aruba's Hamburg and the Aruba's Perdop site, where they both have the same flow sheet and technologies, but they do emit different levels of emissions, and this is similar with Isasmelt sites as well. This is probably one of the first key decision points that have to be made on a project about what level of emissions and the permitting aspects to all this and the level of capital expenditure required to meet the emissions targets for the site. Once you've made that decision point, the other key decision point for the project has got to do with the minor element chemistry control. So a lot of the time the smelting processes, a lot of the design work is not focused on the commodity of interest, the copper in a copper smelter. A lot of the design work and effort goes into the other metals. So controlling the minor elements in the flow sheet, as this does to impact the downstream processes. So in copper smelting, a lot of the focus has to be put onto arsenic, antimony, bismuth, and lead, because these typically impact the tankhouse and operations there. So one of the ways that you can control this is people do control the minor elements in the tankhouse, and they can take out the tankhouse electrolyte and process and purify it to pull out the elements, and you can do things like the EPP circuits and pull out the arsenic from the tankhouse. We find generally that the more effective way is to bleed this from the smelting furnace dusts. So due to the low dust make of the Isasmelt furnace as well as the high level of volatilization in the furnace, you have very high levels of minor elements reporting to the dust, which we can take, bleed and treat. So we offer the oxy-leach technology for this application. So what this means is we can pull out those minor elements at the upfront stage of the flow sheet, and generally the earlier on in the flow sheet you extract the minor elements, the more effective and easier it is to perform. And so you can see that that's an Isasmelt site where they have got very high levels of these minor elements in the concentrates, and they're able to produce the required cathode specifications with the use of dust leaching plants and other technologies there. But this is important consideration when you're doing your flow sheet selection, and it's a bit independent from the equipment you select, because this is has to be done if you want to produce the required cathode qualities at the final products. So the first selection choice, mixing and matching, is got to do with the settling furnace. So the molten slag from the primary smelting furnace does contain levels of entrained metal or matte, depending on the commodity and what goes on. So there's generally two technologies which are used for settling. You've got the rotary holding furnace, which is predominantly a fuel-fired furnace, and you have an electric furnace. In general, the rotary holding furnace can have slightly higher levels of entrainment and metal in the slag, but with good control and operation, it can match that of an electric furnace. The key aspect comes down to fuel versus power costs. The rotary holding furnace also has less operators when you compare that to the MSEF. So both technology have been used in Isasmelt sites, and I'll discuss it a bit more, but this is one of those key decision points as well as which settling furnace you have directly after the Isasmelt furnace. Once you produce that settled slag and you take it from the furnace, the other one that you do need to do is how you post-process that primary furnace slag. So that slag, different ways you can treat this one. So some of the ways that you can do this in toll smelting sites, people can do granulation. So you can granulate the slag with water, you can granulate it with air. That granulated slag can be used in a variety of applications, or it can be landfilled. The other one that people do is slow cooling. So if you do slow cooling, what you do is you enable some of the dissolved metal contained in the slag to come out of solution and form larger metal or matte prills, which you can then recover from flotation. So generally, if people don't do flotation, they granulate and discard. But if you do slow cooling, you can then do flotation. With different flotation technologies, you can achieve different levels of metal recoveries and the final slag discarded. So in general, we found our Jameson concentrator, when processing slag, has the highest overall copper recovery when installed in a copper smelting flow sheet, and we achieve the highest copper recoveries in the copper industry with the technology. So there's different destinations in what you do and you mix and match. Generally, if you do flotation, you'll produce a slag tailings, which we need to be careful of. You either landfill or dispose it. Some sites have used slag flotation tailings in cement production as well. But there's mixing and matching and some choices here as well. A lot of it comes down to the level of recoveries you wish to achieve, as well as the final destinations of that slag and the trade-offs and options there. If we look at the Jameson concentrator for slag flotation, this is one of our other technologies we have within Glencore Technology. And what this does is flotation of your materials. So within the slow-cooled slag, you have got droplets of entrained material, and also you form some on cooling. Now, the majority of the copper losses to the tailings in conventional tank cell flotations has got to do with ultrafine particles, which is a sub 20 micron fraction. A lot of the additional recovery which you can achieve is when you can float those sub 20 micron fractions, and the Jameson cell is able to achieve that with ultrafine bubbles. So we're finding that we can achieve additional recoveries when we put the slag flotation plants in with the Jameson cells there, and this does improve the overall metal recovery, which is quite important for the tighter TCRCs which we're facing in industry. Once you've chosen what to do with the slags, the decision point is the converting technologies. So there's the Pearsmith converter is used a lot in copper smelters, and this has been used for a long time. So this is a batch smelting furnace where you charge the matte, you do 2 stages of blowing, you do a slag blow and then you do a copper blow, and then you produce slags which you then have higher levels of copper than your primary furnace. So generally the Pearsmith converters are very good at what they do, but there are some challenges with them. There's a converter rail which you need to time ladle movements and equipment movements. They're also open and closed to charge and discharge materials, which does lead to high levels of fugitive emissions. They're generally high maintenance because they got the tuyeres and the sidewalls of the furnace which blow the gases into the bath. This does lead to a lot of brick wear around the tuyer line, and they generally have to go through a lot of maintenance because of those tuyeres themselves. A lot of Pearsmith converter rails are leaning towards doing secondary and tertiary off-gas capture and cleaning systems in order to achieve the latest emissions. The other option we have got is the Isasmelt technology. So this is a continuous converting technology. It utilizes a calcium ferrite slag when you compare that to the phthalate slag which is used in the Pearsmith converters. So it's a continuous smelting technology, and it has got improved environmental performance. Now the reason being it's continuously fed and batch tapped. You don't have the opening and closing of the vessel, and as well because the off gas is sealed onto the roof of the furnace, it continually drafts as you charge the materials, which is different from the Pearsmith converters. And it also has enhanced safety. There's less challenges with that on the converter aisle areas. You've got less movements of ladles and simplifies the material handling there. It also has got a higher strength SO2 off gas stream, which does have implications on the sizing and design of your gas cleaning plant and downstream systems. Also requires less hooding, so the secondary and tertiary systems are significantly smaller in the Isoconvert furnace, which does reduce the amount of off gas it's sent for treatment and cleaning. One of the key decision points of your flow sheet is what you do with your converter slag. So whether you have got an Isoconvert or a Pearsmith converter, both of these have got appreciable levels of copper in them. So there's different ways you can handle and treat these. So a lot of the Isoconvert furnaces, the approach is to send the slag back into the Isasmelt furnace to resmelt and recover the high copper contents. When it comes to the Pearsmith converter, there are some different options which have been used in industry and have been installed in Isasmelt sites. So in general, you can cool it and send it back into the primary smelting furnace to resmelt it to recover the copper, or you can do slag cleaning. So there are two technologies which have been utilized in industry. The first one is the slag cleaning furnace technology. This one you charge molten phthalate slag from your Pearsmith converters, and you do slag reduction, so you inject reductants. This can be pulverized coal, diesel or pig iron. This reduces the level of the copper dissolved in the slag, and also reduces the Fe3 plus to Fe2 plus contained in the slag. So in the case of fluid slag, it covers the copper and means that you can produce a low discard slag from the Pearsmith converters without the need to recycle the slag back to the primary smelting furnace. The other technology is that has been used in electric slag cleaning furnace. This uses electricity to heat the bath, and they charge metallurgical coke to the electric furnace. This generally has a higher operating cost compared to the slag cleaning furnace, as metallurgical coke is a very expensive reductant compared to the cheaper reductants using the slag cleaning furnace technology. So there is mixes and matches between the two, but they're generally the options you have got. The other important one has got to do with the Isasmelt Tankhouse, and generally there's lots of steps and processes there. When you're designing the flow sheet, or other considerations when you get into the design is the throughput, as well as the minor elements and the recovery of the precious metal products. So controlling the nickel, the electrolyte, and the other chemistries in there as the feed composition changes, very much like the dust bleeding plant. So, as I mentioned at the start, hopefully I've given you a brief introduction of all the mixes and matches and different things you can do in the flow sheet. Now, every single Isasmelt furnace has got different technologies, configurations and options. So I guess why have they done this? So of course every single jurisdiction has different power costs, fuel costs, labour costs, operating costs and emissions requirements. A good example of this is when we look at the primary smelting furnace and the slag, which is slag handling, which is done there. So in general, we can choose between the rotary holding furnace and the MSEF furnace. So if you look at the power costs for the specific jurisdictions and the technologies chosen, you can clearly see that when the power costs are low, those Isasmelt sites have chosen for a matte settling and electric furnace. When the power costs are high, the sites have generally chosen a rotary holding furnace. The reason being it's power versus electricity costs. The exception to this is the sites where they do brownfield installations, such as the Freeport Miami smelter and the Yan'an copper smelter, where they both had existing electric furnaces and they upgrade the site by installing an Isasmelt furnace. In these cases, they opted to keep the electric furnace to maintain the capital efficiency of the projects. So you can clearly see that the power versus fuel cost has a big impact on the settling furnace technology selection, and this applies to all sorts of other parts of the flow sheet. So to assess this, I looked at some different flow sheets to see and explore this for a particular location. So I picked 4 flow sheets which have been used in Isasmelt sites. So the first site, the first flow sheet, was that used at the Mount Isa mine smelter in Australia. So in Australia, if you look at the costs and the inputs there, generally labour costs are high, electricity costs are high, fuel costs are generally pretty good. And of course, there's capital constraints at times for these sites. Mount Isa Mine is an old historic site, and this plant went through a number of upgrades and installations over the years. So this is where the Isasmelt furnace technology and the rotary holding furnace technology was implemented. Now the rotary holding furnace technology here has a benefit because of the power costs, labour costs and fuel costs in the balance there. And this site has got a very low capital cost, and it has got a very good metal recovery because it uses slag flotation as well. So the advantages here is we've got very high copper recovery, with Jameson cells used for slag flotation. We've got a very low capital cost because of a lot of upgrades, and they use an Isasmelt and RHF furnace. But the disadvantages for the flow sheet is they've got high levels of fugitive emissions, primarily because of the use of the Pearsmith converters. There's also higher fuel costs because we're opting to use fuel-fired furnaces rather than electric furnaces. And there's also challenges with the absolute highest margin concentrates, and that comes down to how the Pearsmith converter slag is recycled back into the Isasmelt furnace, because this impacts how some of the minor elements are bled from the flow sheet. The next flow sheet is one of the other common ones which you'll see, particularly in Zambia. So this is an Isasmelt furnace with a matte-sided electric furnace and a Pearsmith converter. So in this particular flow sheet, the matte-sided electric furnace is used for two duties. The first one is to do primary slag settling, and the other one is to do Pearsmith converter slag cleaning. So both slags are charged into the same furnace, and they add metallurgical coke into that furnace. So it reduces the number of equipment in the flow sheet. In these particular locations as well, the power costs are very low, so it makes the MSEF quite a good choice. So it minimises the number of equipment, and you get very good copper recoveries without the need for slag flotation. You will have much higher copper recoveries if you did slag flotation, but it does have a good copper recovery overall. So the disadvantage for this one is not particularly well suited to locations with high power costs due to the amount of electricity consumed in the electric settling furnace. Higher labour costs as well. The MSEF generally uses a lot more operators on the tapping floor to open and close the tap holes for the slag and the mat there. And it can also have a higher OPEX depending on the configuration, the location and what goes on. Another flow sheet is what we have included for the Rifa copper plant in Saudi Arabia. So this is the Isasmelt furnace with the rotary holding furnace and the Isaconvert furnace. So this particular flow sheet has got very good fugitive emissions because it uses the continuous converting technology of the Isaconvert furnace. It doesn't have a Pearsmith converter aisle. It's got very good flexibility with minor elements in your concentrate, particularly with the use of minor element control processes and plants there. Some of the disadvantages it's got to do with the copper recovery because the calcium ferrite slag being recycled in the primary smelting furnace. This impacts the chemistries there and does lead to a slightly higher copper loss to the slag. It can be mitigated in some options and things there. We have got a higher recycling load of slags because the Isaconvert slag is entirely recycled back into the Isasmelt furnace, and it does also impact some of the operating costs. Depending on the minor element bleeding and control, sometimes you do need to dope some spice or other metals in the anode furnace to get the anodes of the composition you want. The fourth flow sheet, the last flow sheet, is one of the plants which runs really well. So there's a Tuticorin plant in India. While the plant's not currently running for a variety of reasons, not economic or technology driven, this plant is probably one of the world leading copper smelters. This flow sheet's also used in southern Peru. So if we look at this flow sheet, they use an Isasmelt furnace, a rotary holding furnace, Pearsmith converters, and a slag cleaning furnace. And so this particular flow sheet has a low capital cost. The slag cleaning furnace and the RHF are both low cost furnaces when you compare those to the MSEF technology, and they also have a very high copper recovery. And now it does add some additional furnaces into the flow sheet because you have got the SCF there as well, and does add additional molten material handling because you are charging material to that SCF there. So now we've got 4 flow sheets. I did an OPEX and Capex comparison for the flow sheets. So I took a basis for these sites. So I took the paper, as you can see in the bottom there, that was presented at the Copper 2019 conference, and used the exact same concentrate specifications and exact same input costs. I then took the 4 flow sheets, assessed the OPEX for 4 flow sheets for the same composition concentrates, and look at how that impacted the OPEX. So you can see if we look at the flow sheets, there are some differences. So first of all, if we look at this location, it's got moderate to high power costs at $84 per unit. It's got fairly low labour costs, and also there's some other trade-offs there. But you can automatically see based on the power costs and the labour costs, this is likely going to be leaning us towards that RHF furnace and away from the electric furnace technologies. So if we look at the 4 flow sheets, exact same feed materials and things there, you can compare them. Now it's important to note, if we look at the 4 flow sheets, you'll see flow sheet 2 does not include slag flotation. All other flow sheets assessed, including the one performed in the paper, so that's the flash melting furnace, flash converting furnace, and all the other ones there, all included slag flotation. Flowsheet 2 did not include slag flotation. That's for the sole purpose of showing the impact on the OPEX for them. So if we've got these flow sheets, we can sort of see where the flow sheets sit. So you can see if we look at the 4 flow sheets, the lowest OPEX with the highest recovery is flow sheet 4. This is expected because of the power costs, the fuel costs, and the other input costs. This flow sheet is going to have the lowest OPEX. The other 4 Isasmelt flow sheets also had lower OPEXs and better performances than the other plants. The exception of this being flow sheet 2, and this is because of a higher copper loss, and this is entirely due to the selection of slag flotation for the particular location. Other important things to note is that the Mezzo flow sheet, the ASF, ACF, or this is both the Isasmelt flow sheet and that flow sheet both have TSL technologies in them. Key differences in the technology and the operation have led to the Isasmelt flow sheet having a lower overall OPEX. Now, as you can see that there are 4 different Isasmelt flow sheets, and flow sheet 4 is the best one for this location. This may not apply to all sites and locations. So if you just picked a random Isasmelt flow sheet and you tried to assess it against other technologies, you might not be providing the best flow sheet, best assessment, best reflection of the technology. And it's always important to take into consideration the chop, change, mix and match and what you can do with the flow sheet to make them as good as possible. So if, for example, you just compared the flow sheet 3 versus a flash melting furnace, flash converting furnace, you might go there somewhat similar, but if you did flow sheet 4, you'll see there's significant improvements available. So we're doing a lot of this optimization, tweaking and tuning. You can get better flow sheets, and we do a lot of this work for our clients and projects and sites and locations. So I hope that was interesting. I hope you learned some new things, and I look forward to your questions.
Thanks, Stuart. That was really informative. We'll start answering some questions. Hopefully none on Mr. Potato Head. Hopefully everyone understood the analogy. Let's have a look. There's a question here. The presentation was focused on primary copper smelting. Would it be possible to do this for e-scrap as well? Is the data available?
Thanks, Neil. So while the presentation talk was focused on primary copper, the considerations and trade-off and mix and match, like Mr. Potato Head, applies for every commodity and feed material. So e-scrap is a secondary copper material, and there's different flow sheets, furnaces, configurations. So just like that, you can choose different off-gas systems. You can do a straight afterburning, you could do a waste heat boiler for your afterburning, you could do different gas cooling, you do spray cooling and things there. And the converting furnaces, you can do slagging, you can do fuming, you can do the oxy-leach for smaller scale there. So there's lots of options there, and we can do the exact same trade-offs and considerations for e-scrap, along with any other sort of base metal or other sort of metal feed materials which people are interested in. And we of course do additional R&D to develop new flow sheets as well if we identify challenges or if people have those sorts of questions to ask.
Yeah, no, that makes sense. On to the next one. What are the steps for a client to get GT to do a copper flow sheet estimation, and what are the timelines for this?
So I guess the first steps we generally sit down with a potential client or someone who wants to build a smelter and sort of discuss a bit about what their aims, their objectives are. It's very important to understand the sort of feed materials they have, the products they want to make, as well as their future vision and plans. So generally we have a fair few discussions and meetings and some back and forth to discuss this to firm up these things. We then sort of firm up what sort of visions and plans and hopes that they have for their assets long term, because while you design your smelter today to do one thing, you might want to be able to do something else in 5 years' time. And unless we know what that future vision, future plan, or future feed is, it's very hard to design and select flow sheets which enable both the current plans and the future plans to occur. So we have to take all that into consideration to get a bit of a picture of what they want to do and those things. Once we do that, we then firm up a bit about the study, and it's very dependent on what makes most sense. So some studies are very short, 2-3 weeks. Others can take 6 months. It all depends on the level of detail, what they need to know, and those sorts of things. So we can do them very long, very short, or depending. I guess as an example, if you wanted more specifics, we did a flow sheet selection fairly recently for a client on primary copper, and that took about 8 weeks to do it, and we did do a more complete study there, assessing multiple flow sheets, multiple options. We did a lot of discussions on future visions and plans and things. So it was quite a detailed one, that about 8 weeks, but they can be longer and they can be shorter, all depending on what makes most sense for the client and the project.
Yeah, cool. So it's all tailored to the client's needs. No, cool. Next one. Flowsheet 4 was said to be the lowest OPEX and highest copper recovery, with an additional furnace required. Is this the way forward as margins for metals are decreasing? What can GT do to enhance Flowsheet 4 to reduce the capex?
So there's lots of bits to this question. So, how do we reduce the OPEX? So I guess, how do we reduce the OPEX? A lot of this is not just dependent on the flow sheet, but the chemistry design. So depending on what flow sheet you pick on this flow sheet 4, whether you do slag flotation or not, impacts the economics and recoveries. So in general, we know that the Jameson concentrator for slag has got very high recoveries and very low operating costs, and where possible, we generally recommend it for those reasons. It doesn't always make sense for all sites. And so you can do things in the converting area to adjust your recoveries and your operating cost. So changing your iron to silica ratio and the Pearce-Smith converters in Flowsheet 4 can impact your OPEX and your copper recovery. So there is the ability to adjust and tune the flowsheet and the chemistry to further optimize it relative to what we discussed. That also applies to the primary smelting furnace, where different concentrates, different minor elements, different things there, and you can tune some of the chemistries as well as the recycles further beyond what we just presented there. There's a lot of work that can go into that to bring that down even further and optimize even more. That's generally a little bit outside the scope of a more general flow sheet study, but it's more what you'd consider after selecting the flow sheet to really tighten and tune that. And you also do that as you run your plant to bring down your OPEX and improve your recoveries as you run day to day, as your concentrate changes day to day. And so we're probably recommending that's definitely the way forward with your metal margins decreasing, is keeping a tight eye on that chemistry in the process, and that really can have impacts on the overall economics and how you run. Now, in order to enhance recovery, improve the capital costs there. Now, a lot of the capital costs on your smelter is not in the smelting furnaces themselves, but a lot of that comes down to your off-gas systems actually. So good off-gas system selection design really has an impact on the capital costs there, and that's really where we're recommending us focusing on more than the furnaces. So the Isasmelt furnace is very low capital cost, and focusing on other areas of plants is really where a lot more of the value will be driven from. In general, we found from the studies we've done.
No, fair. This question might be similar, but with lower treatment charges and refinery charges on copper concentrates, what do you believe this will do to flowsheet selection?
So I guess as the TCRC on copper concentrates decreases, a lot of the additional revenue you get will probably come from additional copper recovery. So if you look at the copper concentrates, people only pay for a portion of the copper in the feed, assuming a certain level of reduction based on general market conditions. So any additional recovery you get above that is sort of free metal that you haven't paid for but you get to sell. So bringing and focusing on copper recovery is very important with lower TCRCs. So things like, again, the Jameson concentrator for slag is very important there to improve the overall economics. The other one, of course, with the TCRCs is the minor elements. So the penalty elements also get taken into account for the concentrate contracts. So having the ability to take concentrates with high levels of complex materials as well as low grades can also improve the buying selling terms for the concentrates, and extracting more byproducts from the feed can also improve this, and focusing on things like precious metal recovery also improves the economics. So I think there'll be that's probably where a lot more of the flow sheet work will happen. But again, it's very site specific, client specific. Every site is very good at what they do. As we know from all our Isasmelt installations, they're all good and world leaders in where they are in their locations, and their drivers, they're all world leaders in what they do. But it has meant they've landed different flow sheets and things depending on what makes most sense for them.
Yeah, no, that makes sense. Maybe we'll answer two more. What happens in these flow sheets as the copper concentrate grade decreases? How do you manage this in the smelter?
So I guess the question there is a complex one. So if a smelter is trying to maintain copper production with decreasing grades, that means you'll be smelting more concentrates. So this means you'll be putting more sulfur through to the acid plant. So more than likely, you'll need to look at your acid plant capacity. This will be a major bottleneck for the smelter. So if you are expecting concentrate grades to drop, you'll need to assess the sulfuric acid plant capacity and maybe look at that asset and that part of the flow sheet first up to see how you can get more sulfur in there, because that'll be a bottleneck as your grades drop significantly. The other one, of course, is how I handled this in the Isasmelt furnace and other ones downstream. So one of the major advantages of the Isasmelt furnace is we can run and have high flexibility in the furnace. So this means that we can have the exact same off-gas volumes as the grade changes. So if a smelter was to decrease the concentrate grade, you generally go towards higher oxygen enrichment, but you change and shift your furnace energy balance to manage this. So this means you produce the same amount of copper through the same furnace with the same off-gas volume, but you'll have a higher SO2 strength going to the sulfuric acid plant. So this means you stabilize and absorb all the variability in the Isasmelt furnace before it goes to the converter. So generally you'll be producing a constant MAC grade as the concentrate grade changes, and this is very common across our Isasmelt sites. So some of our sites have had huge variabilities, changing concentrate grades of 14–15% copper and con in a matter of hours, and still maintain production and throughput and operation there. Now there are some challenges in know how to get this to work well, but I guess that's generally what we recommend, is taking or absorbing as much as possible in the Isasmelt furnace. The other one, of course, is you can absorb some of those impacts in the converting area. So this means you might decrease the MAC grade in the primary smelting furnace and absorb some of the variability in the Pearce-Smith converters there. So you might need to look at oxygen enrichment and ways to design your converters to absorb some of that variability there. So there's different ways, different things, different options you have, and there is a bit of work and thought that needs to go into designing that effectively to absorb all the variability there. But by doing this, it means that our sites and designs have got very large operating windows and very high flexibility. And this comes onto the TCRC you mentioned before. So if there is a shortage of concentrates available on the market, if you can smelt wide range of concentrate compositions and grades, you can effectively keep the smelter full of concentrate all the time, and that means you can maintain copper production, fixed versus variable costs, and improves the overall economics.
No, thank you, Stuart. I think we have time probably for one last one. Here's a good one. What critical metals can be recovered in this flow sheet?
So I guess that comes down to what's in the concentrate and what you want to design for. So I guess some of the common ones that we've seen people look at recovering, and there are ways and things to think about. Of course, you have your gold and silver from the precious metal slimes in the Tankhouse. You can also produce tellurium from the Tankhouse. You can produce selenium as well from the anode slimes. You can also have, of course, you have the copper. There's some other copper things you could make there if you want to. You can also recover in the dusts. They can generally be enriched in lead, so you can produce lead products. You can produce some zinc. You can also recover bismuth, antimony. There's some common ones as well. There are some other ones as well. You can recover platinum group metals, platinum, palladium, rhodium as well if they're in the concentrates. And there are other things there as well that some people have looked at. Some smelters have taken molybdenum through, so there's some things there you can do. But there's always ways to recover these. But you generally need a bit of a thinking and design. And just because you can recover critical metals doesn't mean it always makes economic sense. So there has to be certain economic drivers to force sites to, the dollars make sense to do these things, and not all sites do that for these reasons. But some sites are looking a little bit more into this as the prices of these metals go up and there's a bit more focus. So it's very site specific and lots of options and things to think about there. But yeah.
Perfect, thanks, Stuart. I think that's all the time we have for the live questions, but our team will still stick around and answer some of the questions in the Q&A. Yeah.
Thank you. Thanks, Neil.